All right, this is Professor Pike. We're going to be looking at, I'm looking to do several videos on steam cycles. We're going to start out with a simple 4-point steam cycle, and we'll embellish it from there. We're going to be using engineering equation solver. You're going to open up a new uh, program, a new file. You'll come up with basically this. Your equations window may need to be resized. I like to keep it so it fits on the screen with a little bit of room around. Drag it off to the right here a little bit. And then we're going to put a diagram in. So we need the diagram window. And that is right there. Diagram window. I didn't want the report window. That's something for a much later lecture. So the diagram window, bring that over here so I can see the diagram window pretty much with the equations window. Maybe make it a little bit. We'll see how big the diagram is. So let's go to pick up a diagram. I made a diagram in Vectorworks. So I want to select everything in that window. Select all. Copy it. And then go back and paste it. Control V. If you have a choice, extended metafile is better. Second best, device independent bitmap, and the third is just a bitmap. So paste it in. That's a little bit bigger than I want it to be, so I can right click on it and properties, and I'll make it 1,000 pixels high, and it will maintain the aspect ratio because I have that checked right there. Okay. And so I want 1,000. Click OK. Move it to around the center so I got some room around it for other text or whatever else I want to do. And then I want to look at the properties again and lock it. That will keep it from moving around once I start putting text on. Right now I'm trying to drag it around. It won't drag around because it's locked. And that way I can keep it static. All right. So now let's go back over and start putting some information in. So I've got another document I'm working with. I'll just copy and paste. That'll save some time instead of watching me type. So we're going to start out with all right, this basic information, and I'm trying to get rid of that cursor thing. Okay, so we've got that done. We've got our state points. Oh, didn't want to be annotating right now. So I got to turn that off. Hold on a second. Back under control. So now what we want to do is take this and convert this into variables. So we'll just copy it. Save us a little bit of typing because we can then just do some editing. Paste it. Mass flow rate equals, so that's going to be m dot. And we're going to just, it's the same everywhere, so we're going to pick 1. M dot 1 equals 50 kilograms per second. Put the brackets around that, the square brackets, that identifies it as a variable with units. Those are the units. And we're going to say m dot 2, 2. All right, 2 equals m dot 1. And we're going to copy that whole section. Command C, Command V, paste again. So that's m dot. We're going to change that to m dot 3 and m dot 4. So m dot 3 equals m dot 1, m dot 4 equals m dot 1. So notice it automatically does a word wrap. If I want to make it all on one line, actually I don't need 16 point. Let's go to 14 point. That will help. And unmatched comma. Okay, that's fine. Let's finish this up first. Anyway, if you can put multiple equations on the same line, and this is the same line as this, it's just wrapped around due to word wrap, as long as you put a semicolon. So that's an equation, semicolon, second equation, semicolon, third equation, semicolon, fourth equation. Pressure at the pump discharge. So that's P, state point 2, equals, and I put a space in there just mostly for legibility. It doesn't really matter for the system. It ignores spaces. Megapascals, but we're in the SI system using kilopascals, kilojoules, so we want kilopascals. So we're going to convert that times, convert MPa, comma, KPa. So as long as you're converting similar units, pressure, you could say MPa to inches of mercury, it would convert it, or to PSIA, it would convert it, or bar. Just as long as, but it won't convert MPa to pounds mass per hour, because that is not the same property. Temperature at the superheater outlet, that is, say 0.3. So we close bracket 3, open bracket 3, close bracket equals 500 C, and the temperatures in the units we want, so left and right brackets. Sometimes you gotta be careful with your touch pads because things move around on you. And quality, which is at the turbine outlet, so that's X at 0.4 equals 0.9, and we will give it a unit of a hyphen, and that will allow us to, for an alternate unit, go back and forth between a factor like 0.9 and a percent. So that would be 90% if we looked at it as a percent. Working fluid is water, so we're going to make this a string variable. And we're going to say fluid $sign after the variable, at the end of the variable name indicates that it's a string variable, equals, and then we identify that with, we surround text for a string variable with a single quotation mark. We use water. We could use, there are 5, I think, versions of water in the properties. So let's go up and look at thermophysical properties for a minute. Thermophysical properties, fluid info. So we've got, for water, we've got 5 of them, I think. So we start with R718. Notice we've got a lot of refrigerants in there. R718, that's water. 744 is CO2. 717, that's ammonia, just for your reference. And then if we come on down to the bottom here, we've got additional steam. Steam International Association for Properties of Water and Steam, Steam National Bureau of Standards, and the one I typically use is water. I'll usually typically use water or steam. Doesn't really matter. And then we can find out over here, we can find enthalpy, density, lots of other issues, conductivity, obviously at the thermal conductivity. CP, CV values are available here as well. We'll get into some of that later. So we could put anything in there. We could put R718, we could have put steam, we could have put water, which is what we did. So now we've got several equations. Basically, we're just stating the values. And we can go ahead and click on the check mark, and it will tell us we've got 8 equations. Excuse me. Why are there 8 equations? Because I have several on one line, right? 8 variables, no syntax errors, okay. And now it changes to the color coding system. We have directives are in green, comments are in blue, and we'll just say this is given data, and we're going to make that red by putting an exclamation point in front of the comment after we put in the quotation marks. Okay, so that's our given data. And we can solve it. It will basically just do this conversion. So that's fine. Let's take a look at it. We got array variables, we got water, and we want to go to the array table. I don't always have luck clicking on this line, so I usually just go up here. This little guy with a red A in it is array table. This is parametric table if you have one. So array table, and we've got our values. We've got mass flow rate. We set it for the entire system as the same, 6,000 kPa, 6 megapascals for the pump discharge, 500 degrees out of the superheater, 0.9 quality out of the turbine. So now what we want to do is start figuring some things out. So let's start with, let's figure out the power produced by the turbine. So we'll say determine turbine power output. Okay, so that's W dot turbine, and that's going to equal M dot of the system. We'll say M dot 3 because we're looking at state point 3 typically for the turbine. That's coming in. It's constant through there, so it doesn't change. So I don't have to worry about that. Otherwise, we'd have to use separate M dot for the turbine in and for the turbine out if we had a bleed, for example. So M dot 3 times specific work of the turbine, small w turbine, and specific work of the turbine equals the change in enthalpy from state point 3 to state point 4. So that's H3 minus H4. Okay. So what else do we want to do? So we don't know H3, we don't know H4. But do we have enough information here to find either of those? We've got the pressure. So let's go ahead and do this. P2, we know. Let's go ahead and say we said that it was going to be, we know pressure losses, so P3 . equal P2. All right. So now what we want to do is we've got two independent properties, pressure and temperature at point 3. So we're going to call real thermal properties because we need enthalpy. We're also going to want entropy so we can figure out what the properties are at state point 4. So instead of having to look them up individually on steam tables and figure out the closest ones, do an interpolation, probably a double or triple interpolation to get to where we want, we're going to use one call to pull all the thermophysical properties that we want at one time. Makes life easier. So we come up here, thermophysical properties again. It stays selected usually when you're working with it within a program and you go back and forth. We're still at water. It will default to acetone, so if you forget, you're going to end up with weird results because it's going to give you properties for acetone, because that's the alphabetically first one. So real thermophysical properties. And we've got temperature and pressure. So those are the default independent properties, but if you don't have that, you'll see we can select any other properties if we have them and they're independent. So we can paste that at the point where we have our cursor, but before we do that, we want the properties at state point 3, so we'll say left bracket 3, right bracket. So our input variables to the left of the colon, temperature at T3, P at P3, and it will give us, we already have temperature and pressure, but it puts that in there anyway, specific volume, specific enthalpy, specific entropy, specific energy, internal energy, and quality. We'll paste it. Saves us a lot of trouble having to put all those array variable information in. So that gives us enthalpy at 3, and then we need enthalpy at 4. So let's go ahead, we can copy and paste this whole thing if we like. Control C and paste it. And so now I pasted an extra copy in, and also an extra line. And we can change the 3s to 4s by selecting the whole thing and Control R. That was working the other day. There we go. Control R. So we got to get rid of this. If it's highlighted, you can just delete it right away or type right over it. Sometimes it comes through highlighted, sometimes not. We're looking for 4, replace with, or excuse me, not 4. We're looking for 3 and we're replacing with 4. And from the cursor position, we only want to do it from within here. You can't select just within there though. If you say replace all, it will go back up to the top and replace all the 3s with 4s, and we don't want that. So we'll just say find next. And occasionally I have this issue where it does this to me. Try this again. 3, change to 4. And usually I have to click, no, I don't want to do that. Click over here somewhere. Now find next. All right, so now we found the next version instance. Replace, scroll through, replace the ones that you want to replace. When it's done, it goes down to the end of the file. It says it's done, and we're good. But what we don't have is the right values here. So we could have gone back up and done it from within the thermophysical properties, or we can just take this and we have a constant entropy process across the turbine. So we change T equals T4 to S equals S4. Okay, and now we need to say S4 equal S3 for an isentropic process. We'll get more complicated later on. And I added it. That's going to cause a choke. All right, so we have S4 and P4 to the left of the colon. That's going to search for that. So let's go ahead and try and check it. 22 equations, 22 variables. That's a good sign. Try and calculate it, and it calculated. So now we've got to put in units. And mine is set up to automatically find or suggest units. I'm going to go ahead. You can have yours set up to do that if you like. I'm going to leave mine like that. Yours, you'll have to reset, I believe, every time you use the program because it's on Citrix, and it will change the preferences. It might retain them for a given program. I'm honestly not sure, but go to Preferences, and we want to go to autocomplete. You want to disable. I've had that on before. It's a problem. I don't like it anyway. Some people like it. Let's see. What do we got here? We want okay. Auto set array units. You can check that. Check units automatically. You want it to do that. Set units automatically where possible. Okay, so it will make those suggestions then and set units for you if you have those checked. So you can check that and change it if you like. All right, so let me go back to, now why did it do that? That's unusual. Let me solve it. There we go. All right, so in the equations window, you should normally just get this. And kilograms per second is not correct. That's kilowatts. And we can compare it with horsepower if we like. Okay. We can also make it a key variable if we like. So a key variable, notice up here we have just one tab. And we might want to highlight it in yellow. So now it will highlight here, and we'll get a new tab up here, and the key variable will show up in there, and we can say power output of the turbine. And click OK. So it highlights it. Go to key variables, puts the text in, and it's highlighted in there. So if you highlight it, it'll be highlighted both in key variables and in the main. It doesn't get rid of the main window. Now, work of the turbine, that is kilojoules per kilogram, so we'll go ahead and accept that. We'll also put in alternate units of, let's see, BTUs per pound, pound mass. Okay, and so that's gives you that. Now if we go to the array table, right up here, the little red A, it's kind of hard to see. We don't have units in here, but what we can do, we can set them in here, or we can set it up in array or variable info. Okay, either that icon or under the options menu. So let's go ahead and we can also reorganize these and adjust the size. This will adjust the size so that it adjusts the column width to accommodate the data that's inside. And now I also want to rearrange it. I want m dot, pressure, temperature, enthalpy, entropy, and then quality, specific volume. Basically, I don't use density when I'm using ease because specific volume is the inverse, and we're using real thermal properties. I get density out right away, unless I'm using a special fluid like a sodium chloride solution for seawater. That does not allow use of real thermal properties, so I typically use density there. Anyway, that looks nice. We're going to go ahead and, so if you notice, let me go ahead and delete that, and delete that. It's correct, the suggestion, but I just wanted to show you. So I can put in individual values in here, but I want all of my variables, array variables, to use the same units for the same variable. So if I uncheck this array variables checkbox, what happens is now it just has H and then the open and close brackets to indicate that's for the array variable, and there's only one instance, not one per however many times we have an array variable. So we can say that was kilojoules per kilogram, and it accepted all the suggestions for everything else when I did that. Let's see, work of the turbine, kilojoules per kilogram, kilowatts for the power, cubic meters per kilogram, specific volume, internal energy, entropy. All right, the units all look good. Click OK, and it's filled out in here. We now have units there. And the other thing we should look at when you're doing your calculations is in the equations window, make sure that there are no unit problems, no other areas. Sometimes it'll have unit problems, sometimes it'll say there's another issue. You need to resolve all the issues before you finish and turn in your program. Okay, so we got the power output. So it's almost at a half an hour on this now. I want to keep it under a half an hour. I actually wanted to make it shorter than that, but let's go ahead. We're going to now determine our state properties at state point 1. So let's say determine thermophysical properties at state point 1. All right. So for state point 1, the way we're going to do that is we'll use call real thermal properties, and we'll figure out what we need from there. So we'll just go ahead and copy the default version, which is temperature and pressure. Copy it, paste it, and then we'll okay, so there it's highlighted. So if I type over it, type over 3, tab in, go make that a 1, hit tab again, find next, and it did that again to me. So sometimes, again, it's problematic, not a big deal. Replace, we don't want 4, we want 1. So I'm going to have to go back. Done. I'll just manually change this to 1, this to 1, and I skipped over this one. So now we've got temperature and pressure at 1. But do we have temperature and pressure at 1? Let's see. So we solve for and got, let's look at our array table. That'll tell us what we have. At state point 1, we have Nada. So where is pressure the same as pressure at 1? Well, pressure 4 is the same as pressure at 1. So we got pressure at 4, and we have we know quality at 1 because it's a saturated liquid at 1. Okay? I should probably add that to this. So I'll do it down here. All right. So we got P1 equals P4. And X1 equals 0.0 hyphen. Okay. All right. So let's try that. Absolute temperature and absolute temperature. I forgot to change this to an X. We're using X, not temperature. X equal X. Okay. Try it again. Everything is good. And we should have a full table for 1. Now we just need to fill out 2. And we'll figure out the work of the pump. The power of the pump. So let's do that. Determine the power of the pump and the temperature at state point 2. And pull all the properties in. And I don't want that in there. So determine the power of the ideal pump and the temperature at, let's be consistent here, state point 2. So the power of the pump, again, m dot of, and I had a different value in here, so we're going to say m dot one. Did we establish our m dots up here? We did. Okay. So m dot 1, specific work of the pump, which is H2 minus H1. We have H1 up here for H2. Oh, yes, that's right. Power. So we have an isentropic process. So S2 equals S1. So we're using S equals S2, P equals P2 for our input variables. And we should be good. Run the calc. And it's trying to tell us kilograms per second again instead of kW. And alternate HP. We can do that again. And we'll make that a highlighted and key variable also. And again, this is an ideal pump. So a real pump, we would have losses, so we'd have to divide by efficiency to get the power needed from the source. Specific work, we'll go ahead and add BTU, BTUs per pound. Right? Okay. No issues. We should have a full table, and I'm going to call it quits. That's 35 minutes. All right.